All right, so now you have a hypothesis that this equals this, and we're kind of stuck trying to figure out why that would be true. So we gotta sort of cross that bridge.
Well, I mean, you can see this being true if R is, for example, 1/2. You can see that it's kind of true.
Okay, why? That's an interesting thing.
Because you can see, like, at 1, so you're going to be approaching 2 here. So 1 plus 1/2, then you're you're kind of a quarter away. Then you add your quarter, and then you're an eighth away, and then you add your eighth, and you're 16th away.
Okay, so you have some intuition that when R equals 1/2, this would be true.
Kind of seems to follow the pattern.
But we're trying to prove it in general.
So simplifying this would be helpful.
Okay. Do you have any guesses? Well, when you're trying to simplify it, but you're trying to simplify it into a very specific form.
Yeah, we're trying to get it here.
Yeah.
I don't really know how to sum powers.
That's all right. There's a formula for it where that infinite geometric series comes from, but in fact, this is the formula. So you're about to prove that formula is true. Yeah, you're rederiving that formula. So we have some pretty good intuition.
Yeah.
Of that these two things ought to be equal, and if they are, then we're done. Because with Fermat's, then. So what can we do? Why? How could we prove that this equals this?
So how can we get the 1 minus R on the top? So maybe could we multiply by a convenient form of 1?
Okay.
Multiply by 1 minus R over 1 minus R.
All right, that seems like it's worth trying. Why? But why? What made you think of that?
Because we want to get the 1 minus R on the top.
Okay, super.
So this is going to leave us with, on the top we have 1 minus R, and on the bottom we're going to have the multiplication later, 1 minus R times 1 plus R squared plus dot plus R at the end. So then we need to figure out what this multiplies out to be.
Okay, good.
So can you remember that? 1 minus R over 1 minus R to the n plus 1. So 1 minus R over, so it's going to be 1 plus R squared plus R to the n for multiplying the 1 through everything.
Yep.
And then minus, you take the minus out, minus R plus R squared plus R to the n plus 1. When we multiply through the minus R, and we factor the minus sign out. So everything can cancel across these two, or subtract out, except for the 1 and the R to the n plus 1. So then we're left with 1 minus R over 1 minus R to the n plus 1.
Okay, great. So this is the expression we actually had before, and we were hoping to prove that it equaled this without the 1 minus R, isn't it?
Yeah.
So indeed, that 1 minus R does cancel, and you're left with this expression for the area under the curve. And what do we need to do now?
And now we need to show that it goes to, what happens when R goes to 1.
Okay. And what happens when R goes to 1?
So when R goes to 1, you get 1 over n. 1 over n plus 1, because you have an extra 1.
Yeah. Nice. So there we go. So some pretty nice work by Fermat. And pretty nice work by you, working through that. I think this is a great example. And it also shows that you know, all these equations that are written down here that all seem obvious when they're written down nicely, like Stephen's programs wrote them down. That it takes a little bit of time to work through, but you did it. So hey, 5. Great work.